Hello all and welcome back. So let us now continue our discussion on BST class, and now let's implement the last function, which is the delete node in our BST class. So let's get started. Now I'm pretty sure that you must have tried the same at your end. It's a little complex, so I will make sure that I'm explaining you each and everything with proper diagram, as well as making sure that the example is also right in front of you and your notes are also proper. Along with that, pretty sure that you must have understood the search and the insert functionality. Please try to just implement them once. Initially, they may seem a little bit hard to do, but believe me, they are pretty easy. Like it is very much similar to the way we did the search function in the starting, right? Just now I'm doing it inside a class. Okay, great. So now let us start with the delete node, everyone. For delete, we will have multiple cases. So let us take them one by one. Okay, let's take the very first case, which is what if there is no tree? So if root itself is none, right? If root is none. So what I'm saying that you have an empty tree and I am asking you to delete. I don't think that's possible, right? So we can easily return none here. So we can easily return none here. Say none was our tree and it will get returned as none only. Okay. So this seems to be one easy case. Let us quickly code it as well. Uh, or let us discuss and we will code it afterwards. Should be fine. Now let's talk about the second case. Okay. Now because we are using recursion, right? I just have to do the work when the node is equals to the data which I have to delete. So effectively what I'm saying is, let's say my tree is something like this: 10, 5, 7, 12, 9, and let's say 8 as well. Okay. So if my tree is something like this, if you are asking me to delete 10, that is somewhere I should do something. Else, I think we can use recursion, right? So else we should be very much good to directly use recursion. We don't have any problem. Okay. So let us first handle the recursive use case. If root dot data, okay, it's greater than the data which you want me to delete. What does that mean? If the data is greater than the data which you want me to delete, then it will be on the left side, right? So I am saying that you are asking me to say delete 7 and I am on 10. 10 is greater than 7. So you should go to the left side and delete. I don't have to worry on this. We have done recursion a lot now, lots of practice as well. All the things are going to get handled by my recursion. So data, what I have to do, I have to just call delete on my root dot left and with the data. Okay. One thing more to understand here is that we should also update root dot left. The reason for that is my overall left can get changed here, right? So for example, if 7 would not have been there and you ask me to delete 5, then recursion will go and delete this 5 and from here it will return none, right? So we should make sure that we are also updating the same. So let me just write it a little bit nicely so that the notes are clear. All I'm saying is whatever recursion does, whatever node or whatever answer recursion is going to give me after deleting the node, I should just update that in my left. So delete, let's say data first and node dot left. Let us take root only. That will be better. We are talking in terms of root. So root dot left. In a very similar way, I can do if root dot data, if it is less than the data which I want to delete, right? Then I think I just need to call on the right side and recursion is going to take care of that. Again, if you ask me to delete 12, then it can be a problem. Recursion is going to return me something. So I should update my root dot write as well. Okay. So root dot write equals delete data and root dot write. Okay, everyone. So I'm sure that till now, each and everything will be clear. Like there should be no doubt. I have not done anything. I have just asked recursion to do the work for me. Okay. So let us quickly code this as well. Let me just zoom out and hide the output. Great. So this was delete and this was search, right? Again, we will be needing a delete helper. Okay. So I'm sure that till now it is clear because our root can change. So I'm creating self dot delete helper where we will be passing down the data and self dot root. Great. So let us create that, everyone. Def delete helper self data and root. Okay. Great. One thing more, I said that we can keep this overall functions private as well. So we can do that if required. That should be easily doable. Okay. So when we actually will be implementing it somewhere, we should keep them private because end user should not have any access to these functions. Okay. These methods. If root is none, return none. If you ask me to delete anything in an empty tree, I cannot do anything. Great. Now let us see what should happen next. If data is less than root dot data. Okay. Then what we should do, we should just call on the left. And recursion is going to just handle the same for me. So delete helper with data and root dot left. Great. Else if, elif, 1 minute. Okay, so we should return the root from here. Or we can keep it, no worries. 1 second. We will return in the end. Okay, so whatever change happens, we are going to return in the end. Elif data is greater than root dot data, then we know we have to go to the right. So root dot right equals self dot delete helper data root dot right. Great. So till now we have handled the cases where I don't have to do any work. Recursion is handling everything for me, right? So I'm calling on the left or on the right. The exciting case where overall the complexity will increase is something when I am on the root. Okay, so fourth case will be if root has to be deleted. So now I'm saying that, hey, I have to do the work because root is something which I have to delete. For example, let's say 10 and say we have 5. Here we can have 3, 7, and say we have some 12, 11, and 13. Okay. Now you are asking that delete say 7 or delete 10. Not 7, sorry. You are asking me to delete 10. Okay, this is the case which you are asking me to do. Now in delete again, I feel that there can be lots of cases. Okay, so let us take them one by one. The very first case, okay, when left and right are null, none. Okay, so what I'm saying right now is, let's say you ask me to delete this 10. Okay, so I am on 10. You are asking me to delete. None is here, and here is also none. I think pretty straightforward. We should just directly return none because I just have this node and you are asking me to delete it. We should just return none here. Okay, and let me write it as well because delete can have multiple cases when we are on the node which is to be deleted, which is to be deleted. Okay. So as of now, we have handled all the other cases. One was when tree is empty. Other was when we have to delete in left. The third one was when we have to delete in right. Now, finally, I am on the node which has to be deleted. Okay. Great. So now let us move forward, everyone, and see what exactly has to be done here. The first case is when again left and right are none. So let me help you visualize this as well, because I want that each and everything should be completely clear. So let's go to the visualizer and let me just duplicate this tab and pay attention now, everyone. Let me zoom in. Okay, this link is already present in your intro to BST file, which you will download from the resources. So you can also do the same, use the same. When I insert this 10, and now I am asking you to delete this 10. Okay. Effectively, what exactly is the case right now? Here, nothing is there, none. Here as well, nothing is there. You are asking me to delete this node. I should be good to delete, right? So what I will do, if you ask me to delete, I will just delete it. This is the node which is there, and it is saying found node to be deleted. Okay, so let me just increase the speed maybe. What exactly it has to do now? Animation is running. Play. And it has deleted the node. Okay, node to delete is a leaf, deleted. Okay, so maybe this is something which we can write as well. That is node to delete is a leaf. Okay, so pretty straightforward case. We can just directly delete it. Great. Now let's see the second case. Second is when either of left or right is none. Okay, so the case I'm saying here is something like this. Let's say I have 10 here. Here it is none, and I have some tree here. In it, I have some tree here. Okay, or 10. Here I have some tree, and here it is none. In this case, let us try to see this again. Okay, I will tell you what exactly should happen. If you are asking me to delete this particular node, and this is none, one of your side is none, then we can actually just return this tree, the tip of this tree, right? So I can just return you either the left or the right, whichever is not none. Okay, so let us help visualize this as well, everyone. Let us see this as well. Let's say, let us play it. Okay, great. So let's say I am adding, let me refresh it. I am adding 10. Okay, let me just improve the animation so that it is not taking so much time. I'm adding 15. And you can see the insert as well. It is exactly the way we have done it, right? Adding 12. Then let's say I add 17. So now we are adding 13. Okay, so yeah, all this operation it is doing. That's why I chose this visualization for the insert and delete, not the other one which we used initially, right? And finally, let's say I'm adding 20 as well. Okay, this is the last one. So it's going to the right. And finally, it will say, I found a position for you. Great. Now pay attention, everyone. If I'm asking you to delete 10 here, don't you think that if I delete this, if this is deleted, this is just what I should return? Root dot right. In a very similar manner. If I am saying if I delete this, then what we should return is root dot right. In a similar manner, if left is there and right is none, then I can just return the left one. Because once you delete this, your whole tree will be just left with what you see, right? After removing the 10. We can see the same in action as well. Let us see what exactly happens. If I delete 10 now, what's going to happen? It's saying it's deleting 10. Let me remove all these scribbles. Yeah, see, this is what your tree will be. Straightforward to understand, right, everyone? So I will repeat it again. If either of left or right is none, then we can comfortably say that, hey, return the other one. Okay, so let me just draw it here as well. Return this, return this. Right, everyone? So when we delete 10, the leftover tree will be returned. Leftover tree will be returned. Great. So pretty short. It is also clear. Let us code this as well, everyone. Else, if so, I am now on root. If my root dot left is none, return root dot right. Okay. Elif root dot right is none, return root dot left. Okay, so this is what we have discussed. Same thing we have just implemented. So till now, I'm pretty sure each and everything will be clear. We have just handled the case. Initially, we are calling recursion. In this case, if we have tree on either of the legs, the right or left, I'm just returning that. Now comes the most exciting case of all, which is when both right and left are present. Okay, so let me add a page and let us see this case now. The fourth variation overall is when left and right both are not none. Okay, so this time I'm saying both are not none. So let us see that as well, everyone, in visualization. This is your overall tree where this time on both sides you have some values. Now we cannot delete this directly because if we delete this, this wall will get lost. Okay, so what's going to happen here will get lost. I hope each and every one of you are able to understand this. Let me show you this in the visualization as well. If you ask me to delete 15 and if I delete this whole thing will get lost, right? So the whole thing here will get lost. This particularly, if I just directly delete 15 without returning anything, I will actually lose the whole tree. Okay, everyone. So I hope this is clear. So now let us understand what can we do. Okay. If we have to remove this for sure, this thing is clear that we have to remove this particular node. Right, everyone? If that has to be done, then we need a replacement. So the main thing is that we need a replacement in place of the deleted node. Deleted node. And pay attention a lot, everyone. This is a little tricky concept. Again, trying a lot to explain you easily. If you are saying that, hey, delete this node, then I should have something back here which I can return. So what effectively I'm saying, if you are saying that, hey, delete this 15, then I cannot delete it directly. I should have some node which is going to replace it here so that my tree still become intact. Okay, everyone? So I hope this is clear. I have to make sure that I'm able to find a replacement. Now, what can be a good replacement? I believe there can be two replacements. Okay, so there can be two replacements. There can be two good replacement for node, right? First, and either of them will work. First, lowest node on right side, or second can be highest node on left side. And I will explain why either of them will work and why they are good replacement. So pay attention everyone. See, if I'm saying that I have this particular tree, which is a BST, and you are asking me to delete this particular node, this node. After deleting, I should maintain my tree and it should also maintain the BST property. What can be a good replacement? Something which is lowest in this particular tree, lowest in this particular right subtree can be a good replacement. Why? Because it will be bigger than everything here. It will be bigger than everything here and smaller than everything here. Okay, so let me show you this as well, everyone. Let's say in this example, okay, in this example, you ask me to delete 10. Okay, you ask me to delete 10. So I delete 10. Now, what can I replace 10 with? Can I replace it with 15? I cannot. Because then 12 is on the right side. BST property violated. Okay, if that's the case, can I replace it with 20? No. Again, 15 is smaller than 20. I have the BST property. Right, everything bigger. Left, everything smaller. I cannot violate this property. So, what can be a good replacement? 12 can be a good replacement. What I said, lowest on the right side or biggest on the right side. So either 12 or 7 can be a good replacement. Why is that? Because pay attention. If I replace it by, let's say, 12, and after replacing, I just say delete 12. Okay, so I will see how we will delete it, but let's say I delete 12. Now, don't you think that this all is making sense? And again, because this was none at one end, this correction will get created. Okay, so we will see if the visualization also does the same thing, but pay attention everyone. 5, 7. Okay, so 5, 7 is smaller than my 12. 15, 14, 20, bigger than my 12. I see the property is still getting valid, the BST property. Similarly, if I just replace by 7. Okay. Now, don't you think the property is getting properly followed, the BST property? 7 is greater than 5, but it will always be smaller than everything on the right side. So that's the overall aim on how can we make sure that we are deleting the right node. Okay. Sorry, we are replacing it with the right node. Now let's see how can we find. So in the current implementation, let's say I'm going with the first one, the minimum on the right side. To find the minimum on the right side, you have to understand one more property of BST. When I go towards the left, value decreases. Okay, let me draw it in the notes so that you are having this thing. So pay attention everyone. Let's say we go with the first one. Okay. When we go left, value decreases. What does that effectively mean? If I start from this particular position and keep on going left, I will get my minimum. Okay. So what I'm saying, start from 15 if you have to delete 10 and keep on going left, left, left. You see 12 is the last one. Okay. Or you can start from left and keep going right. Because in this particular subtree, now I just want you to focus on this subtree. In this particular subtree, the lowest value will always be kept on the left. So if you keep on moving left, you will get the lowest value. And we just need to get the lowest value. So I'm pretty sure now this is a lot clear everyone, what exactly is happening. Once I get the lowest value, I will just update this with 12. And because now I have done this, I will just ask recursion to go and delete this thing. I will just call on this particular tree to go and delete 12 and it will do it for me. I don't need to care how. Okay, so let me write the code and it will be a lot more clear, everyone. Then we are going to see the same. If both of them is not right, then first let's get the minimum larger node. Okay, so the node which is greater, but which is closest. So here I'm going to create a function again, get min node, and I'm going to pass root dot right. Okay, so let us create this function as well, everyone. Def get min node. I will be getting self and a node. What can I do? I will be defining a current where I am. Okay, so from this example, I am on 15 now, and I will keep on going left. So while my left is not none, okay, current is equals current dot left, and you can just now directly return current. So what exactly happened here? We said, let me go and explain that in diagram. We said go to 15, start from 15 and keep on going left till you see this none. Left current dot left is none. Is sorry, is not none. Keep on going left. You will be sure that you will reach to the lowest overall node. Once you reach to this lowest node, return that node. That is what we have done in current. Once you have this node with you, just chain the root data. Root data is equals to min larger node dot data. So now I have changed the data with 12. So 10 in a way is deleted. But now the problem is I have 212 in my overall tree, right? So what I have done here, I found 12. Now I have to remove this 12, right? So I have to just change this 10 by removing. So now effectively 10 is removed. Now all I have to do is just delete this. So for that, I actually am writing a delete function. So I can use that. What effectively I have to do? Root dot right. This is where I founded my founded my minimum is equals to self dot delete. Okay. And we should call delete helper because we know we have to start from the root right only. So I know that I don't have to start from root. I have to start from this particular only, from 15 only. So it will be the data is min larger node dot data, and I have to start from root dot right, and it will handle the same case for me. Pretty sure this is clear. Again, I've moved a lot slow. Let us just see how exactly this particular visualization handles this thing. Okay. If it is also doing the same thing which we are doing. So all I'm doing is I'm deleting 10. Okay, so I will click the button and we will see the visualization in front of us. Let me zoom in a little bit. Great. And I'm increasing the overall animation. Great. So let us delete 10. So it is saying deleting 10, found node to delete. It is replacing it with 7. Okay, once 7 is done, it replaces 7. Okay, so it is doing the other way around. That is fine, no problem. Just that you can do either of them. So 12 is also a good candidate. 7 is also a good candidate. If you want to get to 10, to 7, you could have called on left and then keep on moving right. So yeah, I think this is what is going to help you all, everyone, to delete the node. And we can do it in either ways. And let me write just one last thing. Once we change the data in my node to be deleted, we delete the replacement. Straightforward stuff, something which we have done. You might have to see this part again because it's a little bit tricky, something which we normally don't do, a little complex operation, but again, I'm sure that the way we have done it, you should be able to understand it nicely. Once I've done this, all the changes are in my root. So let me just return the root. Okay, everyone. So yeah, I think this is what we have to do. We can just test it out quickly. How can we test it out? So for the timing, let us see the tree. What exactly is the tree, everyone? The tree is something like this. So 20, 10, 25 and 15. Okay. So let us one by one delete few items and print the tree again. Great. Okay, I removed it by mistake. No worries. 20, 25, 10 and 15. Okay. So let us do one thing. My BST object dot delete. I am first deleting 15. So this will get deleted and we should see 10 as none. See, 10 is none, 25 is none, 15 is not there. So it is working fine. Now let us delete 10. When we delete 10, I think we should see it just like this. So the tree will become something like this when we delete 10. 20, 15, 25. So let us run this. 1 minute. Great. So I'm seeing 20, left is 15, right is 25, and others are none. So it also seems to work fine, everyone. Now let me delete, say 25. Okay. When we do this, we will just see this part. So it should be easy. And we see 20, left is 10, right is none, and other part are same. So this is also working. Now let us do the main part. So now what I have to do, tree was something like this: 20, 10, 15, and 25. If I delete 20, this should get replaced by 25, and our final tree should be something like this. Following all the BST property, it should get replaced by 25. Okay, because here, when I will say root dot right, its left is none only. So we will just return this. Okay. So yeah, let us check this. 1 minute. Yeah, we are deleting 25, right? Okay, so it is saying 20, left 10, right none. Okay. We are deleting 25, my bad. We have to delete 20, not 25. Okay, now it should be done. See now, 25, left 10, right none. So 25, left 10, right none. 10, left none, right 15, right 15. And 15, both are done. So it seems to work fine. Absolutely great. Glad that we were able to write the full logic properly. Now I want all of you to just keep, like, just try to write it at your end once. Okay, you can just follow the other approach, which is to find the highest node on the left side. Okay, you have the overall visualization with you to help. Your notes are also pretty nicely done. Please make sure that you just quickly go through all this understanding and try to code this from scratch. Okay, so great, everyone. I hope you were able to understand everything from this particular approach. I have tried to keep it a lot easy and with the visualization so that it is understandable. Okay, so great, everyone. Let's meet in the next video. Thank you.